know it. But relax. Yeah.
Hi Fabio, you're planning to show something or?
No,
using the whiteboard?
no slides, yeah?
Whiteboard?
Yeah.
Okay, you're an old-fashioned.
This is the format, I think. Everybody's
The
doing.
format is handouts, but.
Yes, they're there.
That's great. Okay. So just wait a minute or two.
Mm-hmm.
So Fabio, just a few minutes, not more than that, and then we open the discussion. And
Yeah. I took notes of what I want to talk about, and I have no clue about how it's gonna take. So let's just chat.
Yeah, and it's not recorded, so you can say anything.
It actually is. I think it's streamed.
What?
It is streamed, I think.
It is?
Yeah.
I thought, didn't we decide not to? But anyways, it's good for people that cannot attend.
Yeah.
I think it's streamed, but there's no way to call in to join the discussion. You can just
Okay, so, but it means that it's also recorded, right?
I think so.
Yeah. There are handouts here. Which you can see here. If you go to one.
Fabio, do you want a water or
A little bit, yeah. Thanks.
you have to do
Yeah,
the
today.
hard work today?
Okay, maybe we should start. So today, Fabio will tell us about supermassive black holes in the Milky Way satellite galaxy. And once again, it's a discussion, so it's not a talk. He will just say a few words to give us sort of the background, and then feel free to ask questions and discuss it. Go ahead.
Yes. All right. Hi, everyone. Thank you for joining this discussion. As I was saying before, I took some notes, and you can find handouts to spread around a little bit. I have no clue about how long it's going to take the introduction, so let's just have a chat. Feel free to interrupt me at any point. So for people who know me well, you know that I mostly do high redshift things, high redshift sources. So the whole fact that we can see the host galaxies here is very remarkable for me. Today we're going to talk about a very interesting galaxy, a satellite galaxy of the Milky Way, Leo 1. So Leo 1 is the farthest and also among the brightest satellite galaxy of the Milky Way. It's at a distance of about 255 kiloparsec. So how many satellites of the Milky Way are there? Well, the surprising question is that it's not completely clear. We know that at least 14 satellites are out there, so we know that their orbits are closed. But they could be up to 69 satellite galaxies in the Milky Way. We know that there are 69 small galaxies up to about alpha a megaparsec away. So this little introduction at the beginning and also the handout is organized in 3 parts. First of all, I will ask the question based on a paper in 2019. Is there, sorry, I can't write. Is there a supermassive black hole in Leo 1? Then we will talk about the possibility of detecting the supermassive black hole in Leo 1 and also in other satellite galaxies. And then we will talk about the possibility of how did it form if it's actually there. Okay? So this is the little plan of the introduction that I thought about. Contrary to other talks that I gave regarding Leo 1, I will be completely agnostic today. Okay? So I'm not necessarily pushing the fact that there is a supermassive black hole there. I will just tell you what we know so far, and then we can discuss later on. So regarding the first part, to be H or not to be H, that is the question. I organized a little, I compiled a little list of objects that we know or we suspect can contain a supermassive black hole at the center. From the right, you can see giant elliptical galaxies. That's an image of M87. We know very well. We took a picture of it. Also, thanks to several people here in the audience and the CFA and BHI in general. We know that there is a supermassive black hole there. Same thing for the Milky Way, of course. We also have an image. The Milky Way is about 1,000 times smaller than M87. Apart from galaxies, big galaxies, then we go in the realm of dwarf galaxies, and that's where the problem starts to be, okay? Because these sources are, the black holes at the center of these galaxies are smaller, so they are harder to detect. Their mass is smaller, they accrete less mass in general. So the M87 has a 5 billion solar mass black hole. The Milky Way has a 4 million solar mass black hole. This corresponds to an Eddington rate of about 0.1 solar masses per year for the Milky Way supermassive black hole. Then for dwarf galaxies, there are about 20, 30 dwarf galaxies with detected supermassive black hole at their center. Typically, they are detected with X-ray emission with optical variability. I chose this particular source, which is Markarian 462. This was detected by the group of Ryan Ecox at Dartmouth 1 or 2 years ago, I think. And this is the smallest dwarf galaxy in terms of stellar mass that is known to contain a black hole at the center. It's not a huge black hole, it's about 2 in 10 to the 5 solar masses, so technically it's not a supermassive black hole, it's an intermediate mass black hole. But this galaxy, which is about 10 to the 5, 8.5 solar masses in stellar mass, we know that there is a supermassive black hole at the center. Then if we go more to the left, so more to lower stellar masses, that's where the real far west starts. It's much harder to actually understand if these sources, these galaxies contain a central black hole. Of course, here I'm talking about central black hole, so a black hole that is more massive and it's approximately at the center of these galaxies. I'm not talking about wandering black holes that are also studied by several people here, Angelo, for example, myself, a student as well. So the reason why it's very hard to detect supermassive black hole or central black holes in satellite galaxies, in globular clusters, is that they are very small. They don't accrete. So getting an electromagnetic detection is very hard. So for the globular cluster case, I took the example of 47 Tucane. A few years ago, there was a dynamical detection of a black hole, intermediate mass black hole that is about 2,300 solar masses at its center. And then we have satellite galaxies. Satellite galaxies are in the middle between globular cluster, dwarf galaxies. They have typical mass of 10 to the 6, 10 to the 7 solar masses in stellar mass. So understanding if there is a supermassive black hole at the center, it's very important. Of course, Leo 1 would be the first with a detection. Leo 1 is actually the first with a dynamical detection of a supermassive black hole at the center. So this dynamical detection was suggested by a paper a couple of years ago by Bustamante and Rosell. She was in Texas at the beginning at that point. So with these images that I chose from the paper by Bustamante and Rosell, I will try to explain in summary why they think there is a supermassive black hole at the center, why they didn't detect it earlier. This is not the first time that they are observing this source, this galaxy, of course, and what could be still uncertain or very uncertain about this. So, first of all, what's different from what was studied before? The classic paper to study Leo 1 is Matteo plus 2008. Okay? This previous study made a very accurate population analysis of the stellar populations in Leo 1. And there is no suggestion of a supermassive black hole there. So what's different? Well, what's different is that in Bustamante and Rosell in 2021, for the first time, they actually studied the central dynamic of the source. That paper and all the previous papers that were done regarding Leo 1 were based on stellar counts on photographic plates. Okay, you have a photographic plate, you count the star, you count radial beams, the stars, you derive what's the stellar distribution of the source, and then you can make some dynamical modeling. For the first time in 2021, they used the integrated light kinematic with an AFU spectroscope, the spectroscopic unit, to actually understand what's going on to the center of the galaxy. So the problem with counting stars from photographic plate is that there is crowding, okay? If this is a stellar field that you have, as long as you are far away from the center, then counting the single stars is not that hard, okay? When you get to the center, typically the central, regarding Leo 1, the center 10, 20 arc seconds, which corresponds to 10, 20 parsec, it's very hard to count exactly how many stars are there. So what do they do in this paper? First of all, they need to find what's the center of the stellar distribution, okay? I'm not an observer, okay? So I read this paper with quite an interest to try and understand what they were doing exactly. First of all, when you have a distribution of stars that is not immediately spheric, and there are not many stars out there, you can see the image of Leo 1 in the 2BH or not 2BH, it's not obvious where is the center. Okay, so what do? Basically, they pick a center here, and they create angular slices here, and they count how many stars are there in every single slice, okay? Then they move a little bit, and they do the process again. And they continue to do the process until they find a center in which the stellar distribution is quite uniform in the different angular slices. So they found a center that is a few arc seconds away from what the previous study found. And this is probably attributed to crowding. So they couldn't, in previous studies, exactly count the number in the 10, 30 arc seconds, central arc seconds. Then what they do is to find the radial surface brightness profile, which is the one that you see in the first image on the top left, okay? So in this image, what you can see is that previous studies were reaching, the previous studies is the M08, so it's the magenta one. They were reaching basically a distance from the center of 20, 30 arc second. Again, this corresponds to 20, 30 parsec from the center. And in the new studies, which is the smoothed curve basically in red, you can see they reach maybe 2 arc second from the center. So they're actually studying the central kinematics of the galaxy for the first time. And what they find is that of a flat central profile. For the radial surface brightness, they seem to see a shallow cusp, a cusp that is shallower, that is shallow, but it's not completely flat. So this was one of the main points that they are arguing for the presence of a supermassive black hole. So what they do is, well, I was talking about the problem of crowding, and I just wanted to mention this fact that I read from the paper, which I find it interesting. In the IFU that they're using for counting stars and measuring the brightness profile, each fiber that they are using, especially in the central part of the galaxy, contains a median number of about 22 stars. Okay, so it's really, really crowded in the central part, and the brightest star among the median 22 actually accounts for about 25% of the stars. So there is a lot of contribution from other stars. So this is the main problem that they are pointing to for not being able to study the central kinematic before. So if you have a look at the second, on the top right image of the second panel in the bottom, you can see that they are comparing their velocity dispersion profile, which is the one in blue, with the velocity profile that was found in previous studies, which is in orange. So not only they find a velocity dispersion that is slightly higher, and in some cases, especially in the central part at about 50 arc second, is actually not compatible with what previous studies were shown. What you can see is that the velocity profile, it's basically nearly almost constant below about 200 arc seconds. And what they argue is the main pointer to the presence of a supermassive black hole in the dynamical modeling that I will discuss in a couple of minutes is actually the central value of the velocity dispersion. So the most central part that they study is about 15 arc second from the center. So I will skip about talking about the different tidal cuts that they do, and I wanted to discuss a little bit the dynamical models that they are using. The dynamical model is actually the first equation that it's reported there. So basically, you have that the dynamical model is basically is based on this equation. This is the radial, the matter density profile. This is the matter, the stellar matter over light, and this is the luminosity density profile that was studied with stellar counts, basically, with integrated light counts. This is the profile of the dark matter. This is the black hole mass, and this is a delta function. So they are basically saying that the black hole is at the center that they found. Okay, so. Regarding the black hole mass, the value of the black hole mass, they are giving it a very wide range. So they're saying that it can be between 0, so no black hole, and about 10 to the 7 solar masses, so a very massive black hole. So the prior is basically flat and very, very large. So what do they do in synthesis? I just want to go to the next session because it's more what I do. They do orbit-based modeling, okay? So they define a potential. The potential is defined completely by this equation. Then they run for each potential about 20,000 orbits. From the simulated orbits, they calculate what's the stellar distribution, the stellar dispersion, and they compare the stellar dispersion at different radial profile, at different radii, with what is observed. Okay. So basically, all the models, they prefer a black hole that is about 3.3 in 10 to the 6 solar masses. This is about, the mass of the black hole that they found, it's 3.3 in 10 to the 6 solar masses. And I want to point out that this is about 60% of the stellar mass of the galaxy, okay? So in normal galaxies, typically the black hole mass is about 0.1% of the stellar mass of the host galaxy. So this is a very, very overmassive object, if it's actually there. The last image that you can see on the top right here, you can see the dynamical mass to light ratio. Basically, the central region is very dominated by the black hole, independently on the model. I won't discuss the different modeling. There are different tidal cuts, so they are saying the galaxy ends here. No, the galaxy ends a little farther. Okay, it doesn't really matter in this initial discussion. So basically, the no black hole solutions are ruled out at more than 95% in all the modeling that they are doing. And the central region is strongly dominated by the presence of the black hole. And to conclude this part, in that paper, they're actually calling for a study with IFU central dynamics of all the satellite galaxy of the Milky Way. Because they are saying, okay, maybe this is real, so we're maybe missing other supermassive black hole in satellite galaxies. So, is there a supermassive black hole? Dynamical modeling seems to suggest it. Okay, we really don't know more than that. So, regarding the second part, this is more what I do actually. So I'm a bit.
I wanted to just recommend maybe some.
Yeah, sure. Yeah.
Because it gets more and more like a talk.
Yeah. No, I just said that anyone can just interrupt.
So, any questions about this part or comments about identifying black holes this way? Do people find it convincing, or is it suggestive? What do people think?
I have a question about the dark matter profile. So, could this huge black hole at the center could it be accounted for by a cuspier dark matter profile? Because this seems totally out of whack. Like
Yes.
60% of the stellar mass seems nuts.
So in the paper, they actually discuss two alternatives. So if there is not a supermassive black hole, you can either have a cuspier dark matter profile. In fact, in the second equation that I reported in this sheet, the dark matter profile is pretty cored. Okay, you have a core. If you remove the core, actually, the model for the supermassive black, I think the model for the cuspier dark matter profile is model 4. It's one of the models that they are showing. So in the paper, they are saying that they actually tried a cuspier dark matter profile, and it still suggests the presence of a supermassive black hole that is kind of the same mass.
How much mass is in the dark matter within the region that we are dealing with? I mean, there is a region of influence, right? For 10, if you take the velocity dispersion, GM over sigma squared will give you a radius of influence. So how much dark matter is in the standard NFW?
I'm not sure how to.
It looks like in the lower left plot, you have 10 to the 6 solar masses
yeah.
of dark matter in 100 arc seconds.
Into the, how much?
6, it looks like.
Okay, well then it's of the same order of magnitude. That's a very good question. Because you can have a diabatic compression by a factor of 3, that's it. So, no black hole, just dark matter.
So you're saying that within 100 arc second?
Within the region of influence, I wonder what that is.
Fabio, you have another question here also.
But the point is that it's not far from what the dark matter provides. So a diabatic compression can do it. And also there are variations, in dark matter profiles.
Right, of course.
There was another comment. Go ahead.
Yeah, I'm not super convinced about the center, honestly. I've been working on open clusters, and they have also very, very difficult center location to find because it's way less spherical. And there, if you don't detect the center correctly, in a way, you have an image that looks like this radial profile with the lower density in the center, and then slightly higher density, and then it goes like normal density. So it could be this bump,
Mhm.
not a cusp, but just the wrong center location.
Yeah, they do mention that compared to previous estimate of the center, they're off by 3-4 arc seconds. I don't know if it's enough to explain it.
Are they assuming the center of light is the center of mass?
Yes, because they count stars. Yeah.
Okay, because another approach is dynamical center, which is a different
Yeah.
way.
No, they find the center by counting stars in the angular slices that I mentioned before. So they follow the light for sure.
But if you look, for example, at the Andromeda, there is this eccentric orbits of the central star clusters.
Mm-hmm.
You know about that? So actually, there are two centers to the ellipsoid.
Okay.
It's not just spherical. So if you make an approximation of a spherical, when it's not spherical, you might get it wrong. Yeah.
Yeah.
Would we also,
Go ahead.
would we also have any guarantee that a black hole that's relatively low mass in quite a very shallow potential well would actually be at the center of mass or the center of light?
It could wobble around.
Yeah.
Yeah.
Because I'm like,
But I mean, it's heavy, so it brings the center with it. You know what I
It's
mean?
not
So
as
like
heavy. I mean, it's-
kinematically, it still
It
influences
defines
the things around it.
Yeah. And
But
also,
where it is in the greater potential might not be in the middle at all. I think its Brownian motion would be really large, as you're saying.
not necessarily. Why would the Brownian motion be high?
I think it would be large because the potential is so shallow, right? So the penalty for being offset is not very high.
But something needs to kick
energetically.
it. Something of comparable mass needs to kick it. So if it dominates gravity, nobody kicks it. I mean, the stars kick it, but very little. Yes, go ahead, Romain.
So Fabio, I'm looking at this velocity dispersion.
Mm-hmm.
So can you remind me, what are the new measurements? Is it the blue or the red?
The blue one.
Blue is the new measurement, right?
Mm-hmm.
Huge error bars.
Yes.
Usually when you look for dynamical evidence for black hole,
Mm-hmm.
the telling sign is a dispersion that increases towards the center.
Yes.
That's kind of the key. But with these error bars, I won't say that there is such a strong indication for sigma
So-
increasing.
Yeah, there is actually another plot in the same paper that I couldn't add for mixing space. So this is the the velocity dispersion profile, if you want to have a look, that they find in the new paper.
There's another one from the same gang?
No, this
It's the
was
same
just
one.
a comparison.
Okay.
So they argue that it's slightly increasing toward the minimum that they measure. It's about 15 arc second.
Well, another thing to keep in mind is these velocities are not different from what you find in binary star systems.
Didn't pass it
So
around
if
before.
there is a contribution from binary stars that is changing with with the distance from the center of the galaxy, then that could affect what you infer from the velocity dispersion, right?
Yeah,
At the level of 10 kilometers per second, you can easily have stars in binaries.
yeah. So I just wanted to say one thing, and then because I don't want to get sidetracked, regarding the velocity dispersion, what Matteo found. Matteo is the previous paper. They investigated, I think, down to 60 arc second or something like that, and they found velocity dispersion that is very stable towards the innermost part that they study, about 60 arc second. This is basically an isothermal density, the velocity dispersion profile. They also, in the same Matteo one, they compare it with other profile, an NFW, for example, and they say that it's not compatible. In the new Bustamante-Rosell that they are studying, 01, what they find, I'm passing the paper around, it's still, as Ramesh was saying, large error bars, but they find a profile that is slightly increasing down to about 15 arc seconds, which is the minimum that they studied the velocity dispersion profile. So is this enough for say that there is a supermassive black hole? Their dynamical modeling suggests it is, because the they actually say that the black hole mass, the presence of a black hole mass, is the only parameter that is best constrained. The dark matter profile, the mass to light ratio is not really well constrained by their dynamical modeling. But I'm really not an expert in dynamical modeling, so I leave it to you. Yeah.
So, I mean, following on Ramesh's question, that was bothering me too. The blue error bars look, to my eye, literally 10 times as big as the orange ones. Do you understand why?
I think it's due to crowding. Okay, so what they're saying, the main point of this.
Even at 60 arc seconds, I mean, 60 arc seconds away, it's not that crowded, right?
60 arc second away is pretty crowded, I think.
Okay.
In the previous Matteo, they reach about 400 arc seconds away. So I would argue that 60 arc second is still pretty central in that galaxy. It's 60 arc second at this distance is about 60 parsec. And the core radius of Leo 1 is about 250 parsec. So I would suggest it's still crowded at that point.
Question, go ahead.
Okay, a question you might not know the answer to. Do you know the image of Leo 1 you put in here? How many arc seconds is that?
How big it is? I would argue about 2 arc minutes. That's a slow one. That's a slow one. Yeah, this is the same image that I used in my presentation. It's about 2 arc minutes. Yeah.
Okay. I don't think in arc seconds works.
Can I ask you just sort of a general question? And in say the Milky Way, there's the central black hole, and then as you go out, there's some sphere of influence, as Avi was mentioning, and then the stars are the dominant contribution to the potential outside of that. It looks like here, outside of the sort of influence of the black hole at about 100 arc seconds, the dark matter is dominant, not the stars. Does that change the story at all?
Well, for both galaxies, it's often the case.
Yeah. I was just wondering how that affects the
Star
stellar.
formation efficiency is very low,
Yeah.
so the potential is dominated by dark matter, basically
So-
almost everywhere.
I mean, I guess the black hole is essentially just a component of that dark
Yep.
matter, but
If I remember correctly, in the Bustamante paper, in the introduction, they were discussing how one of the features of the Milky Way satellites that is still not completely explained is how within all of them, within 300 parsec approximately, so this would be about 300 arc second, there is a fixed constant, fixed matter available, okay? And out of that radius, the dark matter profile and the stellar density profile change among the different satellites. But one of the features is that at about 300 parsec, the stellar mass content and the dark matter content is pretty much fixed among all the satellites in the Milky Way. So I'm wondering if it's something related.
and I guess the black hole would cause the dark matter to form a cusp just through the same Bacall-Wolf process that
Yeah.
the stars form a cusp as they're
Well,
disrupted.
except there is no relaxation for dark matter. It's not Bacall-Wolf. There is no two-body relaxation. So
I see.
it's just a
So what does it
diabatic
do?
As you form the black hole, there is a diabatic compression.
Yeah,
But
Okay, and
it's
that's
not
all. Yeah.
because Bacall-Wolf relies
On the relaxation.
two-body relaxation.
The-
Okay.
So if it's elementary particles, you
The
don't
mass
have
is
that.
way too low. Yeah. Okay.
This is the same reason why they're arguing that probably instead of a single supermassive black hole is not a cluster of black holes.
Okay.
Because first they suggest, okay, maybe this is not a single supermassive black hole, it's just a cluster of small black holes. But they say first, to be able to reach that, you need a very top-heavy initial mass function, so you can form a lot of black hole, and then you need a short two-body relaxation time. And given the stellar density in Leo 1, probably this is not possible, because you wouldn't have the time to
the
form all these
relaxation
black
time is
holes
too
and put them at the center of the core.
That's great.
There was another question here. Go ahead.
About the composition of the black hole, apart from the stellar dynamics, do you have any gaseous dynamics? Like
Any what?
gas dynamics?
Gas.
Yeah.
Yes, this is the second part.
No, but gas doesn't contribute much to the mass, does it?
No, but you can see the profile, right?
Right, you can use
Ah.
the profile to
Yeah,
infer
because
something
from
about the
ARPA, you
potential.
can have the high resolution.
So you're talking about electromagnetic detection. Yeah, this is the second part. Yeah, but in Leo 1 there is basically no gas. No gas left, and there is also no star formation in the last about 1 billion years.
Why don't you continue?
Yeah, so this is a good moment to go to the detection part. So, So, okay, maybe there is a supermassive black hole there, dynamically detected. So how are we going to understand if there is actually there? First of all, we thought about gravitational lensing. Okay, this is the first possibility that we thought. Okay, so we are here, say that we are here, we are observing this galaxy here with a supermassive black hole. We were looking for effects of gravitational lensing created by this mass. Okay, so we did a couple of calculations. You know, the Einstein angle is about 4 gm over c squared dl s dl ds to the 1/2. Okay, so dl s. So say that this is us. This is the supermassive black hole. So this would be the lens, and say that this is the source. Okay, a faraway object. So basically, this is the distance between the lens and the source. This is the distance to the lens, and this is the distance to the source. Okay. So now the problem is that we don't know how far the source is. We are looking for cosmological sources, so galaxies basically, because if you're looking at a star that is within Leo 1, so very close to the supermassive black hole, basically the Einstein angle is infinitesimal, so you won't be able to see it. So you can, assuming that the source is at cosmological distances, so basically the distance, lens source distance to the lens is much larger than the distance to the source. I mean, it's much larger than the distance to the lens, so this is very, very far away. You can calculate Einstein angle that is basically asymptotic, and you get a value that is about 0.2 arc seconds. Okay? So the next question is, what's the chance that there is a cosmological source, so a galaxy, a faraway galaxy, within 0.2 arc second from the position of the supermassive black hole? Well, you can get typical Hubble ultra deep field densities of galaxies. So this is about 0.24 galaxies per arc second square. And what you get is you expect a number of galaxies within 0.2 arc second. This is about 0.03. Okay? So basically, there is a 3% chance of a galaxy being exactly in the Einstein ring of this thing. And we didn't find any, at least in Hubble images that are available, so we kind of forgot about this possibility. The other possibility is that there is a sufficient mass accretion onto this black hole to make it visible. Okay, so instead of requesting a gravitational lens, we just want to observe it electromagnetically. And this is where we got slightly luckier than the gravitational wave, the gravitational lens attempt that we made. Okay, so what's the calculation that we did? We calculated what's the estimated Bondi radius for this source. Okay, the Bondi, the radius of gravitational influence, basically, assuming the CS, so the velocity dispersion, the sound speed, basically, of the galaxy, the stellar velocity dispersion. So assuming the black hole mass, the sound speed, this turns out to be about 200 parsec. Okay. So this is huge. This is basically comparable with the core radius of the galaxy. And by direct measurements, we found about 106 kinematically detected RGB stars, okay, red giant branch stars. Now, RGB stars have a mass loss that is about 10 to the minus 9, 10 to the minus 8 solar masses per year, okay? This is much larger than the mass loss of the sun. It's about 10 to the 5 times the mass loss of the sun, okay? So they're losing kind of a large amount of mass. I won't go into too many details with the modeling that we did. We assumed an ADAF model, so basically we're saying that the accretion rate is sufficiently low, so there are winds, there are large winds that are allowing only a small fraction of the gas to actually fall onto the black hole, and we calculated that of all the available mass, about 6% actually falls into the black hole. And I won't bore you too much, and we ended up with an estimate of the Eddington ratio. Now, the Eddington ratio is defined as the ratio between the actual accretion rate and the Eddington accretion rate. The Eddington accretion rate for this system is about 0.1 solar masses per year, just to give you an idea. The Eddington ratio that we ended up finding is about 10 to the minus 7, 10 to the minus 6, okay? So this is about 1 to 10 times larger than the Eddington ratio on Sagittarius A star. Then we did some SCD modeling with a code that was developed actually by Don Pesce at the BHI. It includes synchrotron, Bremsstrahlung, inverse Compton, and what you find is the plot on the top left in the second page, part 2. So the different lines that you see are bracketing basically the Eddington ratio that we estimated. And what you can see in this plot is that the peak of the SCD falls in the microwaves. The radio part, so the one on the left, is basically not affected very much by the Eddington ratio. It's quite of a robust prediction of the model, while the X-ray part is very, very dependent on the actual Eddington ratio that you're assuming. So these are modeling that we made. We actually requested some time on Chandra to start with, and then on VLA, SMA, HST, archival data, and JWST. And what you see on the right is what we found, okay? So let's start from the left. The orange 2 points are VLA, so that's radio. The red one that falls exactly on the line, and I promise it's not a joke, that's the SMA, so sub-millimeter. The blue ones are from HST, that's archival data, actually, we didn't take that data. And the green one is Chandra, 2 to 10 keV. So, what is this? It's written Pacucci et al. In prep, actually. It's actually ready, has been ready for the last 8 months. We need to decide what to do with that, because we got also JWST data. We are waiting for JWST data, which is going to happen in like 6 months. So what is this? The X-ray data that we got has a luminosity of about 2 in 10 to the 34 erg per second, okay? So at first thought, you say, okay, this is an X-ray binary. It doesn't need to be like the supermassive black hole. First of all, that's possible, but it's unlikely. And let me explain you a little bit. Why? Where is this source that we found all this data about? So this source is about 10 arc second, which is about 12 parsec away from the estimated dynamical center of the source, okay? And the 1 sigma uncertainty in the dynamical center of the source is about this, okay? It's 9 arc second approximately. So as Olga was saying, yeah, there is an uncertainty, of course, in the exact dynamical estimate of the center. Is this a black hole that is wobbling around, like you were saying, like a little bit of Brownian motion? I don't know. What else? Can it be an XRB? Well, there are relations between the Lx, so the X-ray luminosity of XRB, and the radioluminosity of XRB. Typically, they fall within this line, okay? This source is about 3 orders of magnitude above the relation, so it's too radio bright, okay? Where is it on the fundamental plane? You know, the fundamental plane of black hole activity relates a function, say, of the Lx and m and the radioluminosity, and spans about 10 orders of magnitude, okay? So meaning that here there are XRB, here are very bright quasar, M80, no, not M87, like 3C273, I was thinking about this, it's here. So it goes from XRB, X-ray binary to the brightest quasars that you know of. Sagittarius A star is here, approximately midway. Our source is here, okay? So it's not exactly on Sagittarius A star, but it's pretty close. Meaning that the ratio between the radio, the X-ray, and the black hole mass that is estimated makes it compatible with what we are observing with Sagittarius A star. Can it be a background AGN? That's a possibility. If you have a look at the SCD on the top right here, I don't have the image now, but we compared the photometry that we have so far with standard templates for radio loud and radio quiet quasars. So AGN that are accreting a much higher Eddington ratios, and they are very not compatible with it. They are more than 3 sigma, about 4 sigma away from what we expect them in radio loud and radio loud quasars. So we actually compared the photometry that we have with GRMHD simulations for ADAF accreting black holes. This is something that Angelo Ricarte actually did. And the results of these simulations are on the top right panel here. You can see several lines. The lines are for the same physical properties. So we are assuming the black hole mass. We're assuming the spin of Sagittarius A star, I think. We're assuming the ratio, the Eddington ratio that we think this black hole is accreting at. And the different lines are just different angles of view. So you are viewing the central engine at different inclinations. And as you can see, it's actually very compatible with the photometry that we got so far. The only thing that is not compatible is the X-ray, and as Angelo explained to me, it could be an intrinsic problem with GRMHD simulation. They can probably just account for X-ray that are emitted within 100 gravitational radii, while also in Sagittarius A star, most of the X-ray comes from larger regions. And also the last one that I wanted to point out in this part is that with the few data points that we have in HST, and they are spanning about 2 epochs basically. One is 2006, the other one is 2011, so there are 5 years difference. And the infrared variability that we are seeing between 2005 and 2011 2006 and 2011 is actually very comparable with what we are observing with Sagittarius A star. There is a variability of about 2 magnitudes. Is this proof that it's a supermassive black hole? No, but this is just an additional note that I wanted to put.
Okay,
So,
Fabio, let's allow some people.
yes, I'm actually done with this.
Anyone?
Yeah, yep. Well, I'm just curious, so you're saying the X-ray is high, but you could also say the optical is low, right? It looks like the lines on this plot, if I understand right, the yellow is on the bottom envelope of the black lines, which I think once you go past the red point are the top envelope.
Mm-hmm.
And so if you just chose that top line that goes the highest and then go over to the green, it's only kind of 1.3 sigma off the Chandra measurement, which is totally compatible. And so the only thing you miss is the blue points. So is it equally valid to say that blue points are low and the green point is high?
I would agree with your assessment, yeah.
I mean, you could maybe say the blue points are easier to measure or something, so we trust
Um,
them. But if there's a lot of variability.
Yeah, well, it's a question of the physics that makes
Yes.
those. go
So there,
Yeah.
I agree. There, in the theory, that part of the spectrum is also harder to predict. So this is more sensitive to non-thermal electrons and details of how you do your electron heating and cooling in these simulations, which are things that we know we don't do very well. We usually underestimate. And so I think, yeah, that's probably the explanation as well.
Could, for example, what is the uncertainty in the estimated black hole mass? And could that be part of what's not matching? I imagine the reason why these aren't the cheapest things to do, I'd imagine. So you can't just span an entire parameter space of black hole masses, etc. What does that?
We did try a few. Yeah.
And what these were the best when you assumed the.
I don't remember
Okay,
which
so
one.
yeah, so the uncertainty is the black hole mass is pretty large. It's 3.3 plus or minus 2.
Right.
Okay, so it's not compatible with 0, but it's pretty large. Okay, Angelo actually sent me like 20 or 25 something simulations in a grid in which he was changing the black hole mass, the Eddington ratio, electron density, and other parameters. And this model that I'm showing here is for a 3 million solar masses. So it's basically what they are predicting. But yeah, there is a very large uncertainty in the black hole mass in all the parameters, in all the modeling that they do.
How is that uncertainty causing the fundamental plan?
I'm sorry?
How is that uncertainty of black hole mass falls into the fundamental plan here?
Oh, yes, this is a very good question. The fundamental plane point here assumes exactly the black hole mass that they are measuring. Okay, this is assuming 3.3 in 10 to the 6. Okay, the other assumption that goes here is that we are assuming the distance to Leo 1. Okay, because what we measure is fluxes actually, but here the luminosity in X and the radio. You need to go from fluxes to luminosity, so you need the distance. So if you assume everything that they are measuring in that paper, it falls here, okay? If you assume a 2 milli, for example, let's say that it's 3.3 plus or minus 2, so say that it's about 1, okay? We actually did this and it falls here. Okay, so basically, if you move the black hole mass, it moves almost in parallel to the main plane. Okay, so it wouldn't change much here. So it would mostly move here because the mass is only on the horizontal axis here.
Go ahead. There is another question.
Yeah, it sounds like this black hole is still active. So, is there any emission noise you can detect?
Is there emission lines? Okay, so in ADAF mode, you actually don't expect emission lines because it's everything is ionized, and this is one of the main problems that we have with the JWST. So we got JWST time on near spec, which is going to execute like in May next year, or April, and what we are targeting is the following. Okay, so what can it be? What we want to exclude is first a background AGN. Okay, for the reasons that I said before, we don't expect this to be a background AGN. The SCD is not really compatible, but it still could be. Okay, so if we measure the redshift, we are getting a spectrum. We measure the redshift. So at that point, we can say for sure, okay, this thing is in Leo 1, so basically redshift 0, or it's something that is much farther out. Okay, so we want the redshift. But at the same time, we expect an almost featureless continuum because in ADAF mode, everything is ionized up to very large radii, so you don't expect emission lines. So in the near spec spectroscopy, we are targeting Paschen lines, so in the infrared, but we hope not to see them.
Fabio, what about if you take the hypothesis that this thing is in Leo 1, then you kind of know where this source term in the about the, like, redoing that velocity dispersion analysis with that as your middle kind of thing?
So you're
And
saying,
seeing whether that gives you a different profile or a different, like, degree of cuspiness, because,
Yeah.
you know, of the point that it matters what center you choose. Maybe this is telling you where the center is.
yeah. So you're saying you redo the dynamical model, shift in the center, and see what happens.
Yeah.
Yeah, this is something that we can propose to do. Yeah, it's.
I mean, I don't know the degree to which, like, that involves, like, if there's a catalog of stars and you can redo it yourself, or if you have to go back to the images kind of thing.
So the data that they use is public.
Yeah.
I don't personally know how to use the code that they use,
Yeah.
but you know, I'm a theorist after all.
Yeah.
So Fabio, we have 5 minutes. If you wanted to get to your last part.
Yes, so I will do it very briefly actually. Yeah, I will do it very briefly so we conclude with some discussion. So how did it form? Okay, very briefly. On the left panel of the part 3, there is a very nice plot. This is from a paper by Ruiz-Lara, in which they are studying the star formation rate in Leo 1 from now back to the Big Bang, basically. And I will summarize it by saying that something remarkable should have happened in this galaxy about 5.5 billion years ago. You can see that just after the Big Bang, there is star formation, that it goes to low level of star formation, and then something happened that spikes up the star formation. So they are suggesting different hypotheses in this paper. One is that they merge with an ultra-faint like dwarf galaxy. So this is a galaxy that is very faint, not metal-rich. That's why the metallicity of Leo 1 is pretty low. An alternative that they mentioned both in Ruiz-Lara and the Bustamante is that the spike in star formation was caused by AGN activity. So basically, a burst of activity from the central supermassive black hole could have supported some star formation. So something weird happened about 5 billion years ago, and then Leo 1 had a very close bypassage with the Milky Way, which completely turned off star formation. Regarding tidal stripping, this is a paper that we just published with Avi and Yui Ying, who did very, very beautiful N-body simulation. What we were trying to see is test the possibility that Leo 1 was actually a much bigger galaxy, billion years ago, was on the MM-star relation. So the black hole, the stellar mass was about 1,000 times bigger than the black hole mass. So this would put Leo 1 about 10 times smaller than the Milky Way instead of what it is right now. So assume that billion of years ago, this is the MM-star relation. Leo 1 was actually here. Then it got a very close bypassage with the Milky Way. It lost 99% of the stars, and it ended up here, where it is right now. So to make it very brief, what we did is to start an N-body simulation with data assumption, run the dynamical simulation. We did also some analytical modeling, and we see that after 2 passages with the Milky Way at pericenter distances that are comparable with the minimum allowed by Gaia, we can bring Leo 1 from here to here. So not exactly on the point that is on the MM-star relation right now, but within a factor 2, okay? And a factor 2 is not that much, considering that the scatter on the MM-star relation is about 0.5 dex, so it's a factor 3. So I won't say anything else regarding this. I just wanted to mention in the last 5 seconds that this could just be, if the supermassive black hole is there, a very overmassive system. So now in JWST, and now we go back to the high redshift universe, where I'm more familiar with, with JWST we are discovering a lot of sources between redshift 4 and 7 specifically. This is a paper that I just finished. These supermassive black holes are very overmassive with compared to their stellar mass. Instead of being 0.1%, they are 10 or even almost 100% of the stellar mass. And on the right, bottom right panel, you can see the position of Leo 1, which is blue. It's almost 100%. I mentioned before that this was about 60% of the stellar mass of the host. And in JWST, between redshift 4 and 7, you can see all the sources that we are discovering now, and they are departing significantly from the MM-star relation. And finally, the green points, those are actually in the low redshift universe. These are ultra-compact dwarf galaxies discovered in 2017. And these galaxies have a mass, black hole mass to stellar mass ratio that is actually very comparable with what we are assuming for Leo 1. So yeah, I will conclude here, and let's see if you have more discussions.
Final comments, questions?
So one question.
Ramesh, go ahead.
So the JWST data.
Yes.
How do you get the black hole masses?
H alpha, broad line region H alpha.
Are those JWST high Z galaxies, field galaxies, or they're actually dwarf galaxies, separate galaxies?
Okay, so this is a very important and philosophical question. So the galaxies that we are observing now at this high redshift, they are kind of comparable with the dwarf galaxies in the local universe, but they are like big galaxies in the high redshift universe. So they have masses of between 10 to the, let's see, so the black hole mass is 10 to the 6 to 10 to the 8. So the stellar mass is 10 to the 7 to 10 to the 9-ish, something like that.
EHT will not be able to see this one.
What?
EHT, the Event Horizon Telescope, cannot image this.
Leo 1, there was a discussion about observing it.
It's too far away.
Yeah, it may be marginally detectable and maybe fittable by a ring for NGEHT, but it'd be tough.
Yeah, because it's similar to Sagittarius star, but 10 times more than 10, 20 times.
It's 255 kiloparsec, so it's 50 times maybe. Yeah.
Yeah. Okay. Okay. Well, we look forward to web data, and thank you very much.
Thank you.
How close would like 10 solar mass black hole have to be?
In the solar system.
Oh, that's
We can probably rule that out. I mean, the man, not the spacecraft. So the idea of refitting the center based on this seems smart. The thing I worry about is when you go hunting around using the criteria that you're then going to use for something else, then noise will push you towards